In this video, let's take a look at residuals and interpreting best fit. Residuals are the prediction error calculated by subtracting the predicted value from the actual value. It's how far off an actual value is from the predicted value. So in this little picture right here, these data points are plotted and they're not quite on the line of best fit. And that amount that is the distance to the line of best fit from that data point is what we call a residual value. So these two are positive residuals. They have a distance that's above the line of best fit. And this is a negative residual because it's a point that falls below the line of best fit. And the residual amount is just how far away it is from the actual line of best fit that we've already worked on finding in previous lessons. So let's look at an example. If we have a test score analysis and you've already got your mean study time, so that's like your X sub 1, and your mean test score, which is like a Y sub 1, and we've already found our prediction model, so Y sub 1 is approximately MX sub 1 plus B. And they've already figured that all out in Desmos. The residual would be that if we plug in 0.5 hours of study time into this prediction model, we get 62.95. But the actual test score achieved was 63. That means 63 is 0.05 above the predicted amount. And so that's why the residual value is positive, because the actual test score was higher than what was predicted by that amount. And we're going to do one of these on our own in just a second. So if you get a residual plot or you make one, you want to look at this differently than the kind that we've been working on previously in this unit. You want to look at residual plots are positive or good if they have no pattern in the data. They are just scattered around the x-axis, because that means your data is equally above and below your line of best fit. That's what this means. So this would be a good residual plot. This is good. It has no pattern. There are just as many points above, like 1, 2, 3 above the line, the x-axis. Because that's all you're looking at right here, above the x-axis. And then there's 1, 2, 3 below. Let's see. There are 3 below, so notice there's an equal amount above, an equal amount below, and 1 point is right on the line, which is fine. But it's equally scattered around the x-axis. There's no pattern. This is a good residual plot. This would indicate that this regression model is a very good fit for this data. So let's look at one for ourselves. So example 1 says, using the given data set, find the prediction equation and then find the residuals. So we're going to do this the long way for this example, because Desmos will do all of this work for you, but we need to work through a few so that you understand like what it is you're actually looking at. So study hours is going to be your X sub 1. Grade is going to be Y sub 1. So let's just focus on putting in the data first. So put in a table and type in the data. So 2, 5, 1, 0, 4, 2, 3. And then 77, 92, 70, 63, 90, 75, and 84. So you get all your data typed in, and we want the predicted Y value. So we first need to find our regression equation, linear regression equation. So Y sub 1 equals MX sub 1 plus B would be our next step. Okay, so Y sub 1 is approximately M x sub 1 plus b. And let's write that out. So we have y equals 6.08. So let's say 6.1x plus 63.9 is our prediction, our linear regression prediction equation. So what we need to do is find the predicted value. So in other words, if you studied for 2 hours, you would be predicted to get y equals 6.1 times 2 plus 63.9. And if we studied for, so let's figure that out. Now what we can do is type in, to help ourselves save some work, we can type in our prediction equation now that we have it. So 6.1x plus 63.9. And then just replace the x. And I'm going to actually take out the y equals. We don't need that right now. So I was going to pull up a table of values, which you can also do. But I'm just going to show you how I just plug in the 2. And I get y equals 76.1. Okay, so that's my predicted y value. But notice the actual value was 77, and they're not the same. So your residual is how far away it is. So remember that your residual is the actual minus the predicted. You want to keep it in that order to make sure you get the right amount. So actual was 77 minus the predicted, which is 76.1. So that should be 0.9. So notice this takes a lot of work, but we can do it for each one of these. So for the next one, we can say y equals, the predicted equation is 6.1 times 5 study hours plus 63.9, and we get our predicted amount. So let's just replace the 2 with a 5, and we get 94.4. But then check over here. The actual grade was 92. So 92 and 94.4 are not the same. So the difference between them is our residual. So we got to say 92, the actual minus the predicted. So notice that's going to be a negative amount. So if you want to type it in, you could say 92 minus 94.4 is negative 2.4. So that's our residual value. Okay, so let's keep going. So we need to plug in some more values. So let's, instead of typing all of these in, we can use Desmos to help us. So we have our prediction equation. I'm going to pull up a table that'll help me find these much faster. So I'm going to go ahead and type in, let's see, 1 I see goes with 70. And 0 goes with 63.9. And we need 4. So 4 goes with 88.3. And 2 was 76.1. And 3, let's see, let's type 3, is 82.2. So that means if I plugged in y equals 6.1 times 1 plus 63.9, I got y equals 70. And if I plugged in 6.1 times 0 study hours, it would make sense that I get y equals the 63.9. And if I studied for 4 hours, Desmos just did the work for me because I pulled up a table. And y equals 6.1 times 2 plus 63.9. So I got y equals 76.1. And then y equals 6.1 times 3 plus 84, not 84. I was looking over there. Plus 63.9. I get y equals 82.2. Okay. So what we can do is compare those now. So 70 is actually equal to 70. So we have a residual value of 0 for that one. Oop, wrong button. So 70 minus 70 is just a residual of 0. So that one would be right on our line in just a minute. And then, let's see, we have 63 minus 63.9 would be a negative 0.9. We have 90 minus 88.3, which will be 0.7. 75 minus 76.1, which is a negative 1.1. And then 84 minus 82.2, which would be 1.8. Okay, so what we do is once we figure out the residuals, which your Desmos will figure out for you. So we have done all of this work. And if we go back to our original data and underneath it, we got our linear regression equation. There's that little word down there that says plot in the box. Hit that button and what pops up are the residuals. So Desmos actually finds all of those numbers for you. We just did it this one time to show you where they come from, but they're actually right there for you. So actually, I think I missed a number, which is also good to check my work. I needed a 1.7, and I think the rest look good. Okay, Desmos actually also plots these values for you right there on the x-axis. And I don't know, I think on the next example, we're going to plot it on our paper. So let's go to the next page. We found all of our residual values after we found all the predicted values, after we had found the prediction equation. So we have done lots of good work so far. So let's continue example 1. We have the same data, so we're not having to type that in again. We got the predicted value that we can copy over. So let's just copy and paste those down here. And we have our residual values. I'm going to try to nicely copy that down here. Oop, hold on. Let me fix it. Okay, so let me try that again. Copy and paste. So that way we can just be focused on this page. Okay, so now we have our predicted values and our residual values. What you want to do to create a residual plot is you are not plotting the predicted values. You are only plotting the residuals, and it's around the x-axis. So treat it like you're just going above or below the x-axis this amount. So 0.9, I'm just going to plot with the 2. So 2 goes with 0.9. So 2.9. Then I have 5, negative 2.4. So 5 goes with negative 2.4. 1 goes with 0. So it's right on the line. 0, negative 0.9. Right there. 4, 1.7. 2, negative 1.1. And 3 goes with 1.8. Now, if you look at this residual plot, it actually has somewhat of a pattern to it. It looks like it's somewhat quadratic right there. You see what I'm saying? So I would say this residual is not a good fit. So no. Does this indicate a good fit? We would want to say no, because it has a quadratic pattern we can pick out. No, there is a pattern to the plot, and we do not want a pattern to our plot. So this leads us to example 2. One last quick example. Which of the following residual plots represents a model of best fit and why? You do not want a residual plot to have a pattern. That is bad. So you want to look at all of these and see which one has the least pattern I could pick out. So this one looks quadratic, so that's not good. It looks like I could draw a quadratic. This one looks like it's polynomial, so that's not good. And this one looks quadratic as well, so that's not good. So number 3 would be the winner, because it looks like the points are just evenly scattered around the x-axis. Some are below, Some are above and some are right on that x-axis. So we want to say this one is good because it has no pattern that we can pick out. The points are scattered. So let's write the points are scattered around the x-axis. Which is what we want. This is the winner. Okay, so that's it for these notes.